Perfect. So my introduction will be very brief. So let me welcome everyone to our GAMMS test campaign. So this is the second and final test campaign of the GAMMS project. So here is the focus, is the demonstration on the testing of the developments of the GAMMS project. And this is actually the fourth test drive within this week and the second live stream of the session. Before we start with the details, I'd like to briefly also introduce myself. My name is Selim Solmaz. I'm a virtual vehicle. I'm the lead of Control Systems Group here in the Department of Electrics, Electronics and Software. And I am the project manager on behalf of Virtual Vehicle. I would like to call for Ismael. So I think he wants to also do a short introduction to the project and the testing event, and then we can start with the discussions.
Good morning to everyone. My name is Ismael Colomina. I am the general coordinator of this project and the director of geomerics. And I would like to add a few words for all of you to know about the context, the general mode of the project. So as Selim said, we are now conducting the second series of tests for GAMMS. You know, the future autonomous vehicles need special type of maps, so-called high-definition maps. These maps have to be accurate, have to be up-to-date, have to include specific information for the cars to drive by themselves. As you can imagine, collecting this information is very expensive because we need cars for everywhere in the world, and they have to be, as I said, accurate and updated. And we said to ourselves some years ago, why don't we put together the technologies of autonomous driving, high accuracy navigation, and mapping together, so we can produce these maps automatically. So this, what you see here behind me, is the big brother of all this system, where we, as I said, we are bringing together this technology. And we were very fortunate to being able to enjoy, to use the high accuracy service in Galileo, because this is a public service that hopefully will let us produce these maps without any additional infrastructure. So the idea is that when we put together these technologies, we can have autonomous vehicles driving along our roads and collecting information for production of high definition maps. And with this production will be much cheaper, to be done more frequently, and therefore contribute to this new world of autonomous driving.
So I hand over to Markus. He can explain the vehicle, and then later we hand over to Marta to explain the GNSS technology in the vehicle.
So my name is Markus Schratter. I'm working at Virtual Vehicle, and today I'm here at the test driver. But in general, at Virtual Vehicle, I'm responsible for our vehicle demonstrators. So we have different vehicles, we have different robotics platforms, and in this project we are using our Ford Fusion. It's a normal stock car, and we equip the vehicle with different kind of actuators, sensors to be able to drive automated. Like you can see, there are a lot of sensors on the rooftop. So for automated driving, we are using cameras, lidars. In the front, we have integrated radar sensors, and these sensor signals, they are fused then later on for the automated driving. Also, if there are any kind of questions during the drive, I think Selim can answer quite well any kind of thing about the vehicle. Mm-hmm. So this is more or less the vehicle from outside. And inside, for the automated driving, we have a normal PC, an industrial PC. All the sensors are connected, and with this platform, more or less, we are driving automated. During driving, we also have a black box recorder, so we record standard signals which we are sending to the actuators. Kind of basic signals, they are logged all the time. This is more or less the automated driving demonstrator from Virtual Vehicle, and now I will go over the phone for explanations about the mapping system.
Thank you, Marta from geomerics. We are in charge of the trajectory determination, so for to do this, we have here several, I showed you yesterday in the demo, The track we have here, we are using an IMU from virtual vehicle. Then we have this our navigation computer, a Raspberry, with a Septentrion Mosaic receiver. We have also the G3 receiver from Deimos, and we are using also a Java as a reference receiver. And we have a chip skeletal clock connected to the Deimos receiver to get this time. So here you see the splitter of the signal to go to all the receivers that we have here for our testing, and the signal is provided by this antenna. I don't know if some of you were yesterday and the name of the antenna was here, but we changed it to here to have more satellites, more visibility. And then, as my colleagues explained you, we have this mobile mapping system from Leica and this GoPro cameras installed here for the activation of the AGVs. So thank you all of you for coming today with us.
So you see on the screen in the middle, you see the vehicle, how it perceives the world with using LiDAR technology. In the bottom left, you see a camera which points at the front of the vehicle. And there is also a small camera inside of the vehicle, so you see what a passenger would experience when sitting in the vehicle. At the moment, we are at the university campus. Like I said, we will make a few maneuvers to calibrate the IMU, and in a few moments, we will head out into the city for the entire trajectory. So we are now leaving the university campus and start our main trajectory throughout the city. The first part of this route leads us into a suburban environment where we have small buildings, therefore we have good visibility towards the sky. So as you see from the camera, small buildings, very good view to the sky, therefore the number of satellites we see is good, and the accuracy of the positioning is also good.
It's a
We'll make
preview.
one more round in the
Yes.
suburban environment, and then we leave the suburban environment and we'll arrive at the first shopping mall.
Yes. And in this shopping mall area, we have a test permission to drive autonomously. And this is why actually our trajectory goes through there. And there we will actually test our automated driving software with the localization solutions from GAMMS.
So, like during driving, we saw the sensor rotator, and our vehicle uses the sensors to detect objects. So here, as an example, here we have the tram, we have a bus, we have here a pedestrian, here is a car parking, and also all these kind of objects, they are predicted. So you can see here the pedestrian walking, now he's hidden or confused with the car, but all in all cars are predicted, and this information is then used for the planning. For localization, we are using the point cloud. So it's loading. So we have here our three-dimensional point cloud. And what we are doing is with the LiDAR, we are doing the localization. So in this case, we don't use GNSS for localization during driving, we are using the LiDAR. So these thick white dots, they are used for localization of the vehicle, and with this we get accuracy in a centimeter range, so precision quality. This is the localization. And also like here, now you see the vehicle driving, and it's also predicted. So it's trying to use the information of the current state, and if there is a road network, it's using also this information for the prediction. You can see here now the bus is predicted, and it's using more or less the information where the vehicle might go. I started on the steering wheel our system, so now we're in autonomous mode. You can see here a lot of people are walking around the car. As a bus stopped on the left side and people went out. Now here are pedestrians crossing the road. Now here also another bus is driving out, but our vehicle stops because we hear a stop line. And everything is fine, and if there's no pedestrian near the car, the vehicle continues. Also, this is a very special error because also here is a tram. So this is quite complicated in Austria, so the vehicle isn't allowed to drive automated. So I'm, as a safety driver, need to say, okay, the vehicle can go, even if it's possible to detect if there is something. And also, like here at the moment, we have a bit of issues because at the moment we are not driving here a lot of automated, and in the last months, a lot of things changed here. So a lot of plans. So what I need to do is I need to drive here for some meters manually, because otherwise we would stop here. But now we are driving again automated. So also as a safety driver, we need to see, okay, are there any issues, and not all the time our demonstrator can handle all the kind of critical situations. Because also here it's quite difficult because the road is quite narrow and we have here big buses, and we don't want to drive on the opposite lane with our car. So we only restrict driving vehicle on our driving lane. Also, if the software stack would be able to change the lane to the other side. Now here you see there's another bus coming, so our vehicle stopped. That we don't have a collision, so now the other bus is away and we continue to drive. So and now we reached here our first goal. So until here we are allowed to drive automated. So now here we are back on track, and from here on again we can drive automated. What we now can do is we can set our next goal position at the main station. And then we can again engage our system on the steering wheel, the button. And now we again drive automatically. Again, here a bus is detected. Here a stop line, vehicle stops. Also because here the tram is driving, we need to set speed that the vehicle continues to drive.
Yeah, thank you, Markus, for showing the autonomous driving technology. We will now continue our manual drive towards the city center, and there we will have some urban canyons in order to challenge GNSS reception. So we are now making our final loop here in this city center environment, and after that we will go back to the university campus where the entire trajectory ends, and we are back where we started. We are now back on the university campus. Our test vehicle will make some final maneuvers in order for the IMU to get some reference data, and after that we will finish our trajectory on the parking lot where we started. So our test vehicle is now approaching the parking lot, which is the final position of our trajectory. And then we will park here for 10 more minutes in order for all the sensors to have a final reference measurement.
At this instant, the total trajectory for the testing campaign has been completed.